Basically, yesterday we have gone through several things, especially on the electron energy band, where over here we are understanding the concept of conduction for different types of phenomenon. For example, for insulators, semiconductors, and also for conductors. For insulators, we know that the energy band gap, or the EG, is normally greater than 2 eV. Then this actually cause, I think, a lower tendency for the field band electron to be promoted to the conduction band. In contrast, for semiconductors, it has a lower band gap energy, around lower than 2 eV, and this actually can give electrons in the valence band to be promoted via radiation or heating, and cause, in the end of the day, some hole produced after the promotion. So basic comparison between insulators and semiconductors. And we also have looked into conductors, in this case metal. For metal, it has a special, I think, characteristic. It can follow either partially filled band or overlapping filled band theories. This actually depends on the types of, or the number of electrons that the element have. For example, for copper, we know that copper have like around 29 number of electrons. If we actually write the electron configuration following the Pauli exclusion principle, we know that in the end of the day, the valence band will be 3, D10, and 4s1. So since s orbital is partially filled, then that is why for copper it can be categorized as partially filled band, because you have a vacant, I think, slot as well in your orbitals. Okay. Meanwhile, for another types of energy band for metals can be categorized as overlapping bands. So this actually in the case of elements that have, I think, fulfilling the orbitals. For example, magnesium. Magnesium have a valence band of 2p6 and 3s2, which means over here all orbitals have been fully occupied. Okay, and the promotion can only occurs for the filled band state. Okay, so similar explanation or differentiation between conductors, semiconductors, and insulators. And I think energy band, in summary, can be actually maybe noted here. You can see that what makes the difference between all these types of materials. Of course, for insulators, the energy gap is quite large, and that is why there's no promotion of electrons from valence band to the conduction band. Thereby, for insulators, it is hardly to see that this material conducts electricity. Semiconductors, it still produce conductivity, but minimal. This is actually with the fact that it still have a gap, okay, but lower gap, that the electron from the valence band still can be promoted, goes into the conduction band. And finally, for conductors, there's no gap at all. Okay, the electrons can actually promoted from valence band to conduction band directly. Right. So today we are going to look into electron mobility. So what does it mean by electron mobility? As I said in our first slides or a first lecture, that electron, when it moves, okay, it will produce a net of motion, and at the same time it will produce current. So when electrical field is applied, a force is brought to bear on the free electrons. This actually will experience acceleration in the direction opposite to the field. Imagine that if you have materials, okay, you know that each atom has its own electrons and it is actually static. When you actually apply external field, you apply some force externally, what happens is that the electron or the atoms will absorb the energy and the electron will start to vibrate and start to move. So because of the movement, and the movement is actually scattering, it didn't actually move in a very finite direction, then this actually will give, I think, a behavior that we call it as electron mobility. Force on electron is equals to minus E capital E, where E is actually the charge and capital E is actually the potential or the electrical field intensity. If there is no obstacles, then the electron will speed up in the electric field. Obstacles means that if you don't put any impurities, no defects, normally in the perfect crystal, in the pure materials, okay, then the electron will move fastly. In the real solid, electron will be scattered by collision with imperfection and thermal vibration. Of course, as I said, in the real solid, if you have alloys, if you have impurities, so this actually will make the electron collide with the imperfections of the structure, and thereby, I think, produce a so-called friction. So when you have a friction, then this, of course, will produce a resistance, and this also, in the end of the day, will produce a velocity drift. Okay, so velocity drift is actually equals to mu e. Mu e is actually electron mobility multiplied with the electrical field intensity. The unit for electron mobility is always meter square over volt second, and the transfer part of energy supplied by electric field into lattice as heat. So, as we said earlier, okay, when the electrons start to absorb the external energy elsewhere, electron will start to vibrate, it start to move, it start to scatter. Okay, and this actually will produce friction, and of course, it will produce another sort of energy in the form of heater. Okay, so heat actually the secondary effects that produce when you have electron that is moving. This is actually what I talked to you just now. If the electron mobilize or move through a perfect crystal or a pure materials, so it will be smooth. I think the movement will be very smooth. If the crystal is actually contains some impurities, or it is been heat up, if you heat the material, so what going to happen is the interaction between the particles is going to be slightly loosened. Then when you actually apply external force, electrical field to these heated materials, then you will see that the electron will start to scatter. The movement of electrons start to be scattered. And finally, if you have some defects, like for example, alloys and everything, then this also will produce some scattering effect to the electron mobility. Right. So electron mobility also relates with electrical conductivity, because conductivity can be calculated, I think, quite directly by looking at the number of the free electrons multiply with the values of electron, okay, and multiply with the mobility of electron. So therefore, you will see over here the formula as stated: sigma, okay, is equals to N, capital N, where N is actually number of free electrons, modulus E, okay, multiply with mu E. Mu E is actually the electron mobility. So, I'm just want to ask you, what is actually modulus E? Anyone have an idea? What does it mean by modulus E? So just to break the session, can I ask orang yang sama saja saya tanya. Nur Atirah. Nur Atirah ada tak?
Doktor. Ada doktor. Hello?
Yes. What does it mean by modulus E?
Modulus elasticity.
Modulus elasticity chapter yang
Tak tahu
sebelum
tak
ni.
doktor?
Tak tahu
Tak tahu lah.
Okey, tak apalah. Dah mencuba juga tu. Okay. Can I ask another person? Maybe Nur Adriana Ahmad Fadilah. Ada tak? Nur Adriana. Adriana, apa yang dimaksudkan oleh modulus E?
Electricity.
Electricity. Do you think that there is a standard value for this?
Yes.
What is the value? Huh?
Electron mass.
Dia? Tak sure juga. Tak berapa sure. Okay, it's okay. Never mind. At least you try. You say electricity and you were saying that there's a standard values for that. Okay, maybe last person lah. Saja nak tanya. Just nak chit-chat with you guys. Nurul Nadia Mazan. Ada tak Nurul Nadia?
Yes, doktor.
Yes. Nadia, apa dia Nadia? Modulus E apa agak-agaknya?
I think about electron.
Electron?
Electrical. I'm not sure, doctor.
Electrical apa? Dia ada dah. Dah ada orang sebut dah tu. Okey, tak apalah. So nak buat macam mana sebab memang tak berapa sure. Okay, so agak-agak ada yang tahu tak? Kalau ada yang tahu, can you write in the chat box? Kalau tak ada, tak apalah. Okay, alright. So, modulus E is actually a standard value that we call it as absolute magnitude of electrical charge. Absolute. Sekejap saya tulis bagi ingat sikit. Modulus E is actually absolute value, okay, of electrical magnitude charge. Magnitude of electrical charge. Magnitude of electrical charge. It is actually a magnitude. Okay. So, do you think that there's a standard values for this one? The answer is actually yes. So, what is actually the value? Value is actually equals to 1.6 times 10 power of negative 19 coulomb. Okay. Value is 1.6 times 10 power of minus 19 coulomb. Okay. Minus 19 bukan minus 11 tu mungkin nampak dia bersambung dengan saya punya ni. 19 coulombs. Right? Mu E bukan micro ini mu kalau bentuk macam ni. Mu mu bukan miau Okay, so mu is actually mobility. So if it actually refers to mu E, then this electron mobility. Okay, you will also see this later mu H. This actually whole mobility. Apa whole mobility? Nanti kejap lagi kita belajar. Okay, alright. In a nutshell, conductivity, electrical conductivity also can be calculated based on electron mobility or the magnitude of electrical charge. So obviously over here you will see that different atoms, okay, like for example sodium, silver, aluminium, okay, it will have a different mobility values, which also having a different carrier density. Conductivity or resistivity of metals. The resistivity, earlier we, I think, see this in the first few slides. Intrinsic resistivity. Rho is defined as the scattering event due to the imperfection and thermal vibration. So imperfection because of you have maybe the shape of your crystal is not perfect. Okay, impurity, because of you have alloys, you have a doping of different elements inside. Thermal vibration is because the materials actually absorb energy, vibrating, and actually cause the particles interaction between each particles is slightly loosened up. So this actually will give the scattering effect of electrons and will result frictions and resistance. So this resistance is known to be resistivity lah. Okay. So the resistivity total of a material actually depends on if the material experience thermal effect, impurities, and also deformation. Increase with temperature, with deformation, and also alloying. So you will see resistivity of a material will increase if you have increase in temperature, also in increase in the deformation, also with increase of alloying. So rho will increase if temperature increase, deformation or changes lah is increase, or alloying saya buat tanda plus lah alloying ni tambah lah is increase. Right. And examples over here, you'll see that electrical resistivity versus temperature. We have a pure copper, we have copper alloys. Copper alloy that been doped with different amounts of nickel. You have 3% of nickel, 2% of nickel, 1% of nickel. You'll see that as we increase the amount of nickel, okay, the electrical resistivity will also increase. Okay. All right. So influence of temperature, resistivity rises linearly with temperature, okay, due to the increasing thermal vibration and density vacancies. Impurities, okay, for a solid solution, okay, resistivity rho is equals to A multiplied with C multiplied with 1 minus C. C is actually the impurity concentration. A is actually the composition independent constant. And for a two-phase alloy, okay, if it actually exists not in an isomorphous system, then you will see that the resistivity is equals to partially resistivity of alpha multiplied with volume alpha plus, okay, resistivity of beta, rho beta multiplied with volume beta. Okay, influence of temperature and impurities on resistivity again. Presence of imperfection increases resistivity. So if you have imperfections due to the formation of or due to the addition of another element, this actually will produce a grain boundaries. Of course, it is also will produce dislocation, impurities of atoms, and vacancies. So this act to scatter the electrons so that they will take less direct path. Okay, so always remember that resistivity increase with temperature, presence of impurity, okay, and also deformation. Right. Some examples: estimate the electrical conductivity of a copper nickel alloy that has a yield strength of 125 megapascal. So this question actually relates between mechanical properties with electrical properties. So you might heard about some materials that when you actually put some pressure, put some stress, it will actually produce electricity. So this material we call it as a piezo electricity. I think at the end of this lecture you will see that. Okay. So the question actually asks, what will be the electrical conductivity? So first, what you need to do is you need to find out what will be the percentage of nickel that been doped. So over here, yield strength is 125. So 125 you read from here. And this is actually the profile. You get at 125, the composition of nickel is at around 21% of nickel. And from another graph, you can actually detect from 21, okay, what will be the resistivity. So resistivity is actually equals to 30. All right. So from the resistivity, you can actually calculate the conductivity. So we know that conductivity is inversely proportional to resistivity. Okay. So if you actually divide 1 divided by 30, you will get 3.3 times 10 power of 6. Okay, so this is actually the value of conductivity. Any questions so far before we move on to the next one? All right. So materials, materials of choice for metal conductors. We know that we have a different types of metals that is maybe more conducting or less conducting. So how to consider if you want to produce alloys, for example, we have to actually consider whether the materials can conduct electricity with a low cost or high cost. Okay, silver is one of the best electrical conduction because it has an electrical conduction quite high, 6.8 times 10 power 7, but it is highly cost. Okay, copper, it is inexpensive, abundant. It has high conductivity, but it is very soft. Okay, it's malleable. You can actually put some low stress force, and then you see that the copper can easily bend. Okay, copper beryllium alloy. Precipitation will hardening. Solid solution alloying. Cool working decrease the conductivity. So normally this one is best for cooling purpose, but it is because it's very good insulators, but it is not good for conductivity. Aluminium, low weight, more resistant to corrosion, but half as good as copper. And you can also have nickel chromium alloy. it has a low conductivity, which means it has high resistivity. So high resistivity of nichrome alloy is because of chromium. So chromium actually will give higher resistance. Okay, resistant to high temperature oxidation. So normally this one will be used for heating elements. Okay, so I guess maybe we've end the second part of our chapter 10B on electrical properties, basically on energy band and also basic concept of conductivity. We are moving on to a more specific definition and also examples of semiconductivity, semiconductors. So those who are studying physics maybe heard about this or learn about this. I think students in physics also learn this subchapter, semiconductivity. So in semiconductivity, okay, semiconductors, it can be categorized into two major parts. The first one, we have intrinsic semiconductors, and the other one, we have extrinsic semiconductors. This is actually an important part that you need to remember, because I think most of the popular question will ask, what's the difference between extrinsic, intrinsic, right? And then extrinsic also, you can categorize it into different parts, N-type and also P-type. Okay, right. So what does it mean by intrinsic and extrinsic? So the very simple definition for intrinsic semiconductor is that it is semiconductors that mainly built with, from a pure material. Pure materials. Meanwhile, for extrinsic semiconductor, it contains impurity. Contains impurity. Right. Intrinsic semiconductors conductivity defined by electronic structure of a pure materials. Okay, so pure materials that we are talking about is 100% pure silicon and germanium as an examples. Normally, intrinsic semiconductors will be coming from group 4A, from periodic table. Group 4A. Kalau ada periodic table, boleh tengok group 4A. Group 4A. Mana group 4A? Ada dekat situ. So, group 4A, carbon, silicon, germanium, tin, stannum, lead. Okay. Ni antara apa tu, elemen lah. Carbon, silicon, germanium, apa lagi? Tin, lead. Okay, so all these are actually the examples of group 4A. Okay, so compound. Okay, semiconductor. Compound semiconductor, it means that compound. Compound ni, I think it's more than one. If you have more than one elements, okay, normally it will be from group 3 until group 5. Okay, like gallium, gallium arsenic, GaAs, gallium arsenic, or indium, indium antimony, indium Sb lah, right? Group 2 until group 6. Cadmium, sulfide, zinc, germanium. So all these are actually a few examples of intrinsic semiconductors. So don't be confused if I say that I think if we are talking about compound semiconductors, it is not meaning that it contains impurity. Of course, you have like more than one element, okay, if you compare with pure materials. But in this case, you have a combination. Combination. So extrinsic semiconductors, it is electrically conductive, and by definition, it is actually with the inclusion of impurity atoms. As I said, for extrinsic semiconductors, we can categorize it as N-type and P-type. So N-type, it means that you have, for example, silicon, okay, as the base material, okay, doped with any element from group 5A. Okay, what is from group 5A? Phosphorus, arsenic, and antimony. P-type, meanwhile, is actually silicon that is doped with group from group 3A lah. Group 3A. Alright. For example, you have aluminium, boron, gallium. Okay, so these is actually the examples of group 3A. Alright. Okay. So maybe we can look into some examples. For silicon, anyone knows what is actually the number of electron or proton number of silicon? Siapa tahu? Anyone knows what is the proton number of or atomic number of silicon? No, Syafika. Oh, Nick. Very good, very good, very good, very good. Saya baru nak tanya. Dia dah jawab 14. So maksudnya dia ada predictable ataupun dia memang ingat. Okay. So if we write the electrical configuration, okay, we know that kalau kita tulis yang macam sekolah menengah punya, 2, 8, 4. See, it has 4 valence electrons. So let's say that I put Si. So dia punya elektron tu ada 4 dekat luar. Betul tak? So for a pure semiconductors as intrinsic semiconductors, so we say that all this material is made from silicon. So silicon dia share dengan silicon yang lain lah. Dia ada silicon ni juga. Okay, so they are sharing. Ni pun ada silicon yang lain juga. Okay, so macam gitu. Alright. And for extrinsic semiconductor pula, because of it actually involve the doping of another impurities. For example, we have silicon. Lepas tu katakanlah phosphorus. Anyone knows what is actually proton number of phosphorus? Siapa tahu? Boleh tulis dalam chat. Siapa tahu? Phosphorus. 15, 15, 15. Good. Right. 15. So if I write the electrical configuration, 2, 8, 5. You see? Right. So we know that silicon earlier we have 4. And then you have phosphorus. Ada 5. 1, 2, 3, 4. Satu lagi pergi mana? Dia terselit lagi ada kat mana-mana lah situ. 5. Alright. And how about for P-type? We have silicon. Okay. Still 4. Aluminium. Aluminium, berapa nombor proton? Berapa nombor proton aluminium? 13. Good. You are paying attention. Right. So 13. If we write here 2, 8, 3. So aluminium. Okay. 1, 2, 3. So what's the difference between this one? Katakanlah I put this as figure 1 and this one is figure 2. What actually can you differentiate? Saya nak tanya Crystal Chong. Mr. Chong, are you there?
Yes.
Not there.
Yes,
Oh,
chapter
yes.
one here.
Okay, okay, okay. All right. So, what can you, discuss the difference between number one and number two? What can you see? Obviously.
Both can share one electron with the silicon, and aluminum will have two that cannot share.
Two cannot share.
That stay in.
Okay. All right. Actually, we have to understand that the orientation will be like SIP, SIP, or it will like connected with each other. Like for example, this one lah. Okay. So if let's say that over here we see that if I add like maybe just one part over here, so silicon, you will see that it's bonded with one electron from phosphorus. Oh, and then, very sorry. Okay, and then you see that this electron, okay, this 1, 2, 3, 4, 1, 2, 3, it can actually form another interaction with adjacent element of silicon. Okay, silicon here. But you will notice that what? You will have an extra one electron over here. Okay. Meanwhile, for number two, figure number two, what actually can you discuss? Siapa ni? Fatin Fakihah. Fatin ada? Yes, okay. So Fatin, how about number two? What can you see? Obviously, I said that one can be occupied to form interaction with silicon. Another one also can form with silicon. This one. But what can you see from number two? Is there any possibility? Like how many bondings that it can form with silicon?
3 bonding.
Only 3.
Uh.
Phosphorus?
4.
4. It can form 4, but at the same time we have an excess. One electron here, excess. Isn't it? So 3, it means that we have lacking less electron. We have one that is excess electron, another one is less electron. So that is actually what does it mean by n-type and p-type. So n-type, it means that you have an excess of electron. Meanwhile, for p-type, you will have less ataupun poor lah, kita cakap poor amount of electron. Okay. So this actually can be say that you have more excess electron. So excess of electron is actually good because you can actually have more electron mobility as compared if you have less electron. But it all depends on the application of the materials. Right. So superconductors is a material that exhibits zero electrical resistance under certain condition and expel a magnetic field completely. Okay, so superconductors, I guess maybe later on we will learn also about this. So material that exhibits zero electrical resistance. So this actually happens if it exceeds the critical temperature, okay, or the critical point. Okay, so materials, okay, that will have zero electrical resistance, 0R lah, 0R, okay, when it reach critical point. All right. So what does it mean by critical point? So each material has its own critical temperature. So if you low down the temperature. So what happens is that it will repel. It will become resistive. So when we say that elements or materials that have more electrons, we can call it as to have free electrons. And when the materials actually have a less electron, or if the electron have been migrated or promoted, then it will leave a hole. Okay, so these two terms need to be clear. We have free electrons and also hole. Free electrons will form negative charge. Okay, hole will produce positive charge. And free electrons will be located in conduction band. Meanwhile, for hole, normally it will be located in the vacant electron state in valence band. As I explained earlier, intrinsic semiconductors, we know that these actually semiconductors that is produced, okay, from elements that is pure. Okay, it doesn't have any impurities, no impurities. So what will be the conduction? Electrons have to be jammed, okay, across the band gap into the conduction band to find conducting states above Fermi energy or band gap energy. The energy needed for the jump may come from heat or radiation at sufficient small wavelength. An electron promoted into conduction band leave a hole as a positive charge in the valence band that can also participate in conduction. Okay, all right. So for intrinsic semiconductors, okay, normally if you have radiation or heating, so what's going to happen? The electrons over here will be promoted to here to form negative charge. Okay, and over here this will form a positive charge. Right. So how actually we can calculate the conductivity? Okay, so based on my explanation earlier, the number of free electrons and the number of holes produced in the intrinsic semiconductor is equal. So holes, number of electron, N is actually number of electron, P is actually number of hole. Okay, for intrinsic semiconductors, it is always happen that number of electron will be equal to the number of holes. You have one electron that is being promoted going to conduction band that produce free electrons and leaving another vacant space as a positively charged as holes. Okay, so it will be equal. All right. So the conductivity of intrinsic semiconductors can be calculated as sigma equals to N multiplied with magnitudes of E multiplied with mu E plus P multiplied with modulus E, magnitude E, multiplied with mu H. Okay, so this is actually the components of free electrons, and this is actually the components of holes produced. N, as I said, is the number of electron. Okay, so modulus E is actually a standard number, magnitudes of electrical charge, which is equals to 1.6 times 10 power of negative 19. Mu E is actually the modulus of mobility, electron mobility. P is number of holes multiplied with electron magnitude, still the same value, multiplied with hole mobility. Okay, all right. So this is actually an example for intrinsic semiconductor. You have silicon bonded to own materials. So silicon, 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 silicon. Okay. So if it is been applied with electrical field, so what's going to happen is the electron will be promoted and it will leave a hole. But I think, as I said, the number of holes and number of electrons produced from intrinsic semiconductors after being applied with electrical field will be the same. It will have one. It will produce one whole, one free electrons. Okay. All right. So similar explanation, as I said. So number of electron in conduction band can also be calculated by this formula, but I don't think that is an important thing to memorize. Conductivity, electrical conductivity, this one, I think this one is quite important for you guys to remember. Silicon have a band gap energy around 1.1 eV. Okay. 1 out of every 10 power of 13 atoms can contribute an electron to conduction band at room temperature. Conductivity of an intrinsic semiconductor, I think have been mentioned earlier. Sigma is equals to N multiplied with modulus E multiplied with mu E plus with P multiplied with modulus E multiplied with mu H. Electrons are more mobile than holes, so modulus E is greater than modulus H. In an intrinsic semiconductors, a hole is produced by the promotion of each electron to conduction band. Therefore, we know that in intrinsic semiconductors, number of free electrons is always equals to number of holes. Okay. So N and P increase exponentially with temperature, whereas modulus E and modulus H decrease about linearly with temperature. The conductivity of intrinsic semiconductors increases with temperature. So this actually depends on the different materials, like for example, metals. Okay, so maybe one last slide before we end our lecture today. So for intrinsic semiconductors, conductivity versus temperature. So data for a pure silicon, conductivity will increase with increase of temperature. So this is actually opposite with metals, because as we said, for metals, if you increase the temperature, then it will actually produce friction, resistance, and after that will reduce the conductivity. So that is why for intrinsic semiconductor, it is completely in opposite with the theory just now. Okay, so I believe for extrinsic semiconductors, we are going to look at this tomorrow. Hopefully by tomorrow, I'm not sure. Yeah, I don't think that we can finish the. Maybe we can finish the whole thing by tomorrow, and but I'm not sure whether we still can have a quiz tomorrow. I will let you guys know, right? So before we end, is there any question that you would like to ask? Anything? Right? So if there is no question, then I will thank to everyone for giving time to listen this lecture today. I will stay back as usual if there's any question arises. But if there's no question, thank you very much. See you tomorrow. Goodbye and Assalamualaikum warahmatullahi wabarakatuh.